Hi, this is Dr. Graves from the CSUN Geography Department. I'm back with part two of the Solar Investment Curve Return on Investment Lab. And so here in cell J2, what we're going to do is just type in equals, and we're going to reference the cell that had our monthly price increase, which was simply AB15. And so you see it here in cell J2. And so to get a time over time increase, it's just J2, what you've already had, plus J2, and then you can freeze that, and then you see it increases by a little bit, and as you go through a full 12 months, you will find yourself up to a 3% increase over the years. So just copy that to the rest of the column. The monthly efficiency column, column K here, is the efficiency of the solar panels themselves. When the days are short and the sun angle is poor for solar generation, you may only get about 60% efficiency out of the maximum. And then in June, when the sun stays up longer and the sun angle is most direct, then you get peak efficiency. So in order to calculate the amount that a system produces on a monthly basis, you'll need to multiply the monthly efficiency by the total output of the panel at peak performance. Click in our system output that is monthly, which is 1,460 kilowatt hours. Make sure you freeze that or fix it and press enter to get 860 or 76 kilowatt hours for that month, and then you can copy that formula all the way down, and you will see that peak performances are in June. Another element of calculating this solar cost curve is the degradation of the panels themselves. When you buy them, they're at 100% peak efficiency, but over the years they degrade. And so that is something worth taking into account as well. Many of the solar panels built in 2023 have a estimated life usable efficiency at 25 to 30 years, and our cost curve only goes up to 20 years, so we should still be okay for our purposes. So the first month we'll have no degradation. We assume that it's going to be at peak performance when installed, but then the second month that formula will change because we expect a small amount of efficiency degradation, and that is over here in cell AD11, and you can press F4 to freeze that. We'll start with that, and then add is the previous month level of degradation, and so the previous month in this instance is the very first month, which is cell M2, which was 0. We will copy this down, and we will see a slight increase in degradation as we move down. So go ahead and copy that to the rest of the column, and we would see after 20 years that there's a degradation of about 24%. So still at 75% efficiency. And then, of course, the next thing to do is to multiply the monthly system kilowatt hours and subtract the degradation from that over the life of the 20 years in our study. And to do that, place your cursor here in cell N2, and you will have the total amount at peak efficiency subtract from once again the peak efficiency for that month, but then you're going to multiply that peak efficiency by the degradation amount. And the first month the degradation is 0, but there will be a tiny amount of kilowatt degradation in the second month, and then at the end of all of these months you'll be losing close to 24%. And you see here in row 241 in the 91st month that the peak efficiency in January would be 876 kilowatts, but you're losing basically 24% because the panels are old, and now you're only producing 667 kilowatt hours per month. Now we're getting to some of the more interesting results in terms of our kilowatt hours production from our solar system. As we'll see, I'm going to scroll over here a little bit. In the winter months, when the sun is low and our demand is high in an effort to heat the house or whatever institution or building that you're looking at, there will be a deficit. So in order to figure that out, we have to subtract our degraded output from our monthly demand. And we see in this case that we are putting out in January 876 kilowatt hours a month, but our demand in January is over 1,000. And so our system finds itself short in that month. But in some of the months, particularly June, as we'll take a look here, we find that we're generating substantial surpluses, and over the course of the year that our surplus will be over 3,000 kilowatt hours. So just copy this all the way to the rest of the column and move on now to the green columns here, which include many of the monetary values that we're going to assign to our production of electricity. So the next thing we need to take a look at is the cost of energy. It's 20 cents, but we're going to see that over time electricity cost goes up. And so for the first month it's just 20 cents, but in subsequent months it will go up a fixed amount. And one estimate had that electricity costs were going up at about 3% a year. 3% divided by 12 on 20 cents is this figure here, 0.0005. And so fix that, freeze it, and you see that it goes up 1/10 of a penny. But if you copy all the way down through our 20 years, that we can expect a kilowatt hour to cost 32 cents. So over the life of the solar panels, their costs will change. And so here's two columns that are almost not necessary, but we'll put them down so we can get an idea. So the electricity cost to us is the 20 cents times our monthly demand, so $203.20 in our first month, and then how much did we generate, which is the kilowatt hours that we generated including the degradation, and then we want to multiply that by 20 cents. And so for this first month we have a deficit of about 25 bucks. So we can copy that all the way down. Our electricity bill, we can calculate that two ways. One would be to multiply the kilowatt hours by our surplus kilowatt hours, and that would give us a number, or we could simply subtract R2 minus Q2. And then that gives us a deficit, outflow of our money of $28. Copy that to the rest of the column. So it's nice to see the cumulative electricity costs. So how much in total did we pay over the years? And so the first month is that it cost us $28, but then subsequent to that we have to reference our first month and add to it the cost of our second month. So we made a little bit of money on our electricity bill, $19.12, and so over 2 months we only paid out about $9. And if we scroll copy that all the way to the bottom, we begin to see that overall the electricity company would have sent us back to us $7,500, which would be go a long way towards paying for the solar system itself. The monthly payment would be something that we might be interested in calculating, and that, of course, would be what we paid on the loan, which is $200 per month, and then we want to add that to that our electricity bill. But in this case, since our electricity bill is negative, then we probably should take the monthly payment, which is $200, multiply that by -1 to make it negative, and then add to that the outflow of our electricity bill. And so we should get a negative monthly outflow of $200, and then whatever our electricity bill. The second month, the electric company has paid us $19.12, so it's less than that. So go ahead and copy that down. That might be of some interest to you. In those months after our loan is paid off, we start to see a positive outcome. And then once again, we can repeat this sort of cumulative accounting. The total we paid in the first month was $228, and then we want to add to that what we paid in the subsequent months. And so after 2 months, it's $408, and then here at the bottom is how much money we paid over the 20 years in the system. This final column is really the most interesting of all of them. So this is the total cost of the system, and then from there we'll be able to begin to see exactly when the balance of payment comes to zero, when we've paid the system off essentially, and then how much money that we would hopefully earn by this investment. So we put a down payment of $5,000 on there, and to that we added the total cost of our loan, which is the $15,000 that we paid plus the $3,000 in interest, so that's $18,000.22. There's the formula up at the top, and around this I really should put parentheses, because then this is the total amount we paid, but because the electricity company is paying us some money to us, we need to subtract what our electricity generated is, and in this first month it's $175.20. So we will click on that and press enter, and so working backwards we can begin to estimate the break-even point. So in the subsequent months, what we want to do is subtract from our initial overall cost then simply how much electricity that we generated. And from this point on, we can copy that down all the way to the bottom, and we see that this is a positive number until we get somewhere around the 92nd month. And I think it's just peculiar that it should basically pay for itself around the same time that we begin to stop having our loan payment. And then, even though this is negative, I guess we could flip it all around with a -1. At the end of the 20 years, so the 240 months, we find ourselves in the surplus, about $40,000. So this is a really good investment. Our break-even point comes in about exactly the same month that the 93rd month. It looks like that the loan pays itself off. Now, of course, all of these can be manipulated. If the loan costs more, if the panels degrade worse or better than before, if the cost of electricity goes up, all of those things you can manipulate in this spreadsheet, and it would create a different outcome for you. The only thing that you would have to be cognizant of is that we stopped calculating anything over here at a 5% interest rate and a $200 payment, etc. on the loan. Everything else, when you manipulate it over in your assumptions panel here, everything else would change. Perhaps the daily kilowatt hour usage goes up or down, all of those sorts of things, the size of the system that you put on the roof or in the yard. All of these can be manipulated. So your assignment is simply to replicate this and send with it a paragraph explaining what you have done. This concludes this tutorial.